In this video we look at damped harmonic motion. In the previous two videos we looked at simple harmonic motion, and with simple harmonic motion we have had to assume that there was no air resistance to the motion. In this case we improved the model by including an air resistance term where the air resistance is proportional to the velocity of the object. So, we're going to consider one example where we have a particle of mass 2 kilograms which is attached to a fixed point A by a spring of natural length 0.5 meters and modulus 16 newtons. The system is initially held at rest on a smooth horizontal surface as shown in the diagram, with the spring 0.7 meters long. The particle is then released, and after t seconds the extension of the spring is x meters. And we're to assume, to begin with, that there are no resistive forces, and we have to prove that the motion is simple harmonic motion and state the amplitude and period of this motion. So, for this first case then, as always we need to have a general time diagram which clearly shows the equilibrium position as well. So here's the diagram for an arbitrary time t after the particle has been released from rest. We will suppose that at this time the extension of the spring is x meters, which means that the displacement of the object away from its equilibrium position is x meters. In the diagram we are treating to the right as being the positive direction for the displacement, so it is therefore also the positive direction for both the velocity and the acceleration. The only force acting on the object is the tension in the spring. So Newton's second law applied to the right is going to give me minus t equals the mass 2 times the acceleration x double dot. Hooke's law tells me that t must be the modulus 16 times the extension x divided by the natural length 0.5. So we've got minus 16x over 0.5 equals 2 times x double dot, which simplifies down to x double dot is minus 16x, which is exactly the equation of SHM with omega equals 4, which means that the period of the oscillation will be 2 pi divided by omega, or pi by 2 seconds. The amplitude of the motion, well, the motion is starting from a position when the object is at rest and the extension of the spring is 0.2 meters, so the amplitude of the motion is 0.2 meters. Now, an improved model assumes that the motion is resisted by a force of magnitude k times v, where v is the speed of the particle and k is a positive constant. We have to prove that the motion is described by the equation x double dot plus a half k x dot plus 16x equals 0, or d2x dt squared plus a half k dx by dt plus 16x equals 0 if you like. So again we start off with our general time diagram, and again we need to put the positive direction for velocity and acceleration into the diagram, and we need to add the forces acting on the object. So we've got the tension in the spring trying to pull the object to the left, and we've also got the resistive force which is in the opposite direction to the velocity of size k times the velocity. So applying Newton's second law, we have minus t minus k x dot must equal 2 times x double dot. Again, exactly as before, t is going to be minus 16x over 0.5 minus kx dot equals 2x double dot. So we've got 0 is 2 times d2x dt squared plus k times dx by dt plus 32x, and divide through by 2, we obtain exactly the equation we're looking for. So we've now got to describe the subsequent motion in the two cases. First of all, k equals 20, and then secondly, k equals 12. If k equals 20, then the equation becomes d2x dt squared plus 10 dx by dt plus 16x equals 0. And this equation has auxiliary equation p squared plus 10p plus 16 equals 0. So p must be minus 2 or minus 8, which means that the solution of the differential equation, the general solution of the differential equation, is x equals pe to the minus 2t plus qe to the minus 8t, where p and q are constants to be determined. Now we've got some initial conditions, and we know that when t equals 0, the value of x is 0.2. So that tells me that p plus q must equal 0.2. Differentiating the expression for x, we have x dot, or dx by dt, is minus 2p e to the minus 2t minus 8q e to the minus 8t. But when t equals 0, we know that the object is at rest. So we've got dx by dt must be equal to 0. So we've got minus 2p minus 8q must equal 0. And if we solve the pair of simultaneous equations we've got, we obtain p equals 4/15 and q is minus 1/15. So the solution of our equation is x equals 4/15 e to the minus 2t, take away 1/15 e to the minus 8t, which can be rewritten if we take out a common factor of 1/15 e to the minus 2t. We see that we've got 1/15 e to the minus 2t times 4 minus e to the minus 6t. We've also got dx by dt is minus 8/15 e to the minus 2t plus 8/15 e to the minus 8t. And there's a common factor there of 8/15 e to the minus 2t times by e to the minus 6t, take away 1. Now looking at the expression for x, if t is bigger than 0, then e to the minus 2t is definitely bigger than 0, and 4 minus e to the minus 6t is definitely bigger than 0. So we certainly know that x is always positive. But looking at the expression for x dot, or dx by dt, 8/15 e to the minus 2t is certainly positive, but e to the minus 6t take away 1 is a negative expression. So dx by dt is negative. So we know that x is certainly positive. We know that dx by dt is certainly negative. What's more, x is certainly smaller than 4/15 e to the minus 2t. So it's certainly going to tend to 0 as t tends to infinity. So our displacement time graph for the particle is simply going to be a decay style curve, and what we have in this case is that the motion is heavily damped. We've lost all signs of the oscillation. If on the other hand we have k equals 12, then the differential equation becomes d2x dt squared plus 6 dx by dt plus 16x equals 0. So that's got an auxiliary equation of lambda squared plus 6 lambda plus 16 equals 0, which gives me complex roots, lambda equals minus 3 plus or minus root 7i, which means that the general solution of that differential equation is something of the form x equals e to the minus 3t times by p cos root 7t plus q sine root 7t. Again, we need to find the values of p and q using the initial conditions. So when t equals 0, we know that x is 0.2. So that gives me p must be equal to 0.2. And if I then differentiate, I'll need to use the product rule to differentiate this time. I've got dx by dt is minus 3 e to the minus 3t times by p cos root 7t plus q sine root 7t plus e to the minus 3t times by minus root 7p sine root 7t plus root 7 times q cos root 7t. Putting t equals 0, we know that the particle's at rest, so dx by dt is 0. So we've got minus 3p plus root 7q must equal 0, which means that q must be 0.6 divided by root 7, or 0.6 root 7 over 7. So we've got x is e to the minus 3t times by 0.2 cos root 7t plus 0.6 root 7 over 7 times sine root 7t. So what we've got here is we've got an oscillation formed by the trigonometric functions, but the size of this oscillation is certainly decaying because of the e to the minus 3t term. So in this case we've still got an oscillation, but the size of the oscillation is decaying, and this is called light damping. And for the final part of the question, we're asked for what values of k will the motion be lightly damped. So our differential equation was d2x dt squared plus a half k times dx by dt plus 16x equals 0. The auxiliary equation is lambda squared plus a half k lambda plus 16 equals 0. And we will obtain light damping if the solution still has an oscillating element to it. And if we have the oscillating element to it, the auxiliary equation must have complex roots. So we need the solution of the auxiliary equation to have complex roots. In other words, we know that b squared minus 4ac must be negative. The discriminant must be negative. So we've got a half k squared, take away 4 times 1 times 16 must be negative. In other words, a quarter k squared must be smaller than 64, or k squared must be smaller than 256, which means the value k must be between minus 16 and 16. However, we know from this question that k is a positive constant, so that tells me that for light damping I need to have k lying between 0 and 16. If k equals 0, then we've got no resistance term there at all, and we're back to the initial pure simple harmonic motion that we had in the first part of the question. If k equals 16, we're at the critical point between having light damping and having heavy damping.